thing, how you might interact with our office, and then tell you a little bit about kind of why toxicology exists, because a lot of people think, toxicology, what? You know, in fact, when I was studying it in graduate school, my grandmother asked me if I was cutting up dead bodies. And you know, that is an area of toxicology, but certainly not what I do on a daily basis, thank goodness. So my background, I actually grew up just outside of Houston, went to one of the small area high schools, one of those places that is like 3,000 people and 6,000 cows. So went to A&M for my undergraduate, have a degree in chemistry, and then went to the University of Alabama at Birmingham for my PhD. Actually studied bone loss during spaceflight and had a graduate fellowship, so I spent my summer here at JSC working in the biotech program. And then Columbia happened right about the time that I finished up graduate school, and unfortunately they weren't really hiring in the sciences here at NASA, so I got a job with the State Environmental Agency in Austin. And they taught me toxicology and risk assessment kind of on the job. I had the pathology background, I had the chemistry background, so fairly easy to combine the two. Torin McCoy, who is now my branch chief, had actually worked in that group as well and knew that I wanted to get to NASA. My supervisor there knew that as well and introduced us. And so when they had a position open with the contractor Wiley, they hired me on, and then I badge switched, came over to NASA a couple years later, and have been here for about 7 years now. So I took over the group when John James retired a year and a half ago. It's hard to imagine that that much time has passed. So if you see my name, I'm the one who is leading the group. The guys, there are 4 guys on my team, and they're the ones who actually do the hard work, so give them all the credit. So what do we do? Well, one of the things that you might hear are SMACs and SWEGs, and those are the limits that we set. So SMACs are the spacecraft maximum allowable concentrations for air. And basically, the EPA and the state will set similar guidelines for concentrations of air for just walking around, outdoor ambient air. The difference is that the population that they have to protect is very diverse, right? They have to protect children, they have to protect the elderly, they have to protect those with pre-existing health conditions like asthma. I'm very fortunate in that I have a very specific group of people that are pretty healthy and in a predefined age range. So ours tend to be a little different from that perspective. The other perspective is you have folks who set occupational guidelines, which is closest to what we do. We're basically setting exposure limits for the astronauts, and that's their job. But our exposure durations are different from occupational guidelines. So most people in a factory will go to work, they'll work for 8 hours a day, then they come home, and they're exposed to completely different things, right? So 8 hours a day for 40 hours a week are their typical exposures. Whereas on station, I have crew that are enclosed 24 hours a day for a 6-month period, right? So the durations that we set SMACs for are very different than what you would see in a typical occupational or environmental setting. For an environmental setting, when I have people walking around the ship channel, I want to protect them for their lifetime, right? In this case, I just need to protect the crew for the period of time that they're on station. So we actually have several different time durations, and some of them are historic. 7 days were based on original shuttle mission durations. Then we moved to 30 days because we started having longer ISS interactions with shuttle, and then we went to 180 days for the 6-month missions that we have on station. We've recently started developing 1,000-day SMACs, considering exploration and looking at something like a trip to Mars. We also have short-term 1 hour and 24-hour limits that are set for contingency situations. So those are when you have a spill on board and you might be exposed to something for a short period of time while you're cleaning it up. We might allow a little bit of extra exposure in that instance, and we might even allow some types of symptoms that would be an annoyance that you wouldn't want to have continuously for 180 days, but something like a headache while you're cleaning something up might be acceptable for a short time. We have very similar standards for water, and they are on a little bit different time scale, but again, they pretty much relate to mission duration. So we have a 100-day SWEG is what we call them, the Spacecraft Water Exposure Guidelines. And these are very similar to EPA's MCLs, or maximum contaminant levels. And so we set these with the National Research Council, their Committee on Toxicology. It ends up being kind of like a dissertation defense. We go to them and we recommend, based on the literature, here are the limits that we propose to set, and we defend that to them. And then they come back and they give us recommendations for, well, did you consider this, and did you think about that, and maybe you should add this type of assessment, and we kind of go back and forth until we agree on appropriate limits, and those are published in books, physical books by the National Research Council. And then I'll talk a little bit about how we deal with exposure to mixtures on board. So you might see something if you get any of our monthly updates about T values. And that's basically how we deal with mixtures of chemicals, right? So we're setting limits for each individual compound. So say benzene, right? We set a limit for benzene and say if you are exposed to less than this number, then we expect it to be safe. What do you do when you have multiple compounds that all might cause the same endpoint? How do you deal with that? And that's the t-value concept. So basically, we take a measured concentration in air, and we get a value from monitoring data. We take the limit, that spacecraft maximum allowable concentration or the water exposure guideline, and we ratio those. And if you are below your limit, that ratio should be less than 1, right? And hopefully a lot less than 1. That's the goal. And so you take all of the compounds that might have the same endpoint, so everything that might cause respiratory irritation, or everything that might cause liver toxicity, right? And you group all of those chemicals together, and you take this ratio for all of those individual compounds, and you sum them together. And if the sum is less than 1, then you know you're good, right? If the sum is 1 or greater, then you know you might have to start looking at something. What is elevated, what might be potentially contributing to an effect. So again, the air is deemed safe if all of those values are less than 1. Yep.
Would T be toxicology or something else? What's it stand for?
It's basically a hazard quotient. So why it's named T, I can't, I don't have a good response for that. A lot of people will use an HQ rather than a T value, but in all of our reports you'll see it as a T. So yeah, the overall toxicity is a good way to think of it. So this is what it'll look like if you see it in any of our reports. And so we will take it based on endpoint. So this is mucosal irritation, carcinogens. Luckily, you'll see that there's no bar there. Respiratory injury, visual disturbance, all of these types of things. Respiratory injury is the one that we have here that's the highest, but you'll see that the value is 0.2. So we're well below 1. And then when we take all of these, we will actually sum the whole total and get a total t-value. And even that, in this case, is well below 1. And that's typically what ISS air looks like. It's actually very, very clean. It's a lot cleaner than what they're breathing when they're walking around Houston, to be quite honest. And you can see that we do this on a monthly basis, and then we wrap it up for the year as well. So does that make sense? You don't have any questions about that? All right. Go ahead.
This one may be hard, but I know that because they're in a controlled environment and the air is purified, if you will, and it's cleaner, as you said, than what they walk around here. So then normally as we're walking around, because we're breathing in and eating and doing stuff, you build immunities. So once they're up there and they're up there for a year, does their immune system now not make them, that degrade in immunity so that when they do come back here, some of the stuff that they're going to now start sucking in, they're not immune to anymore? So
that's an interesting question. Most of these don't directly impact the immune system themselves, most of these chemicals. So some of them can. So benzene is an example, right? That's one that will cause a leukemia. Fortunately, one we don't see on station. But
my
I
question.
get your question. Your point being, if you're not having these exposures for a period of time when you come back and then you're exposed to them. So you have enzymes and things that will take care of these chemicals when they come into your body. And generally, those pathways aren't broken as far as we understand in spaceflight. And so we've not seen anyone come home and have any troubles adapting. But it's a good question, you know, and one that I don't think that we've looked at sufficiently to get a good handle on it. Good question. Yeah.
And just a logistical question. You said that you guys generate these reports once a month and then once a year. So do you guys do the air testing like the first day of each month?
Oh,
Like,
that's a
is
good
that
question.
how it's done?
So we generate monthly reports. So, okay. For the monitoring, we actually have several different types of monitors. So we have a real-time air monitor called the air quality monitor that samples every 3 days. It's actually every 71 or 2 hours so that we get different times of the day over the course of the year, different days of the week and different times of the day. So that's actually downloaded to us weekly, and we put out those data weekly. Those data are summed up into a monthly report that we generate. Then we also collect archival samples that are grab sample containers that are under vacuum, and they will open it and suck in an air sample, and those come back with crew each increment. So then I also issue increment reports so that that particular crew knows what they were exposed to during the time that they were there, and that combines both air and water information. So water, again, generally every week we get TOCA information, which is the Total Organic Carbon Analyzer. So we're looking to see trending in the water. But then we also bring water samples home and analyze them on the ground and can look at a wider range of chemical compounds. And we get that every 6 months or so when crews come back. And then we also report yearly. So we kind of, we have lots of methods for monitoring, and then we roll all of those data into things that are meaningful to different groups. And different groups are looking for different time frames, and so kind of depends on the needs of the customers. Make sense?
Yeah.
So if you're not getting data that you need, let us know.
Who are your main customers?
So crew office is one, right? So again, the crew wants to know what they've been exposed to. So they've actually requested those monthly reports that we generate. That's not just tox, it's micro and radiation and all of the environmental sciences kind of rolled into a single monthly report. They've actually requested that those be uplinked to them on station so that they can see what they're being exposed to while they're there. ISS program obviously is interested, and they fund the majority of our laboratory dollars come from the ISS program to make sure that we're operating at safe levels. When we start to have increases in the water, for example, they're the ones who are interested. They're the ones who have to pay for the upmass for changing out the filtration beds. So they're our primary customer. Yeah.
Who supplies the monitoring hardware?
That's a great question. So again, ISS typically pays for it. The monitors themselves come from a wide range of expertise and locations. So there are the small businesses through the SBIR program that develop monitoring. Some of the monitors are prepared by our laboratory. We do the science testing, and then the engineering group in SF actually does the hardware preparation and checks it out for the technical, does it turn on, and those types of things. The Jet Propulsion Laboratory develops a lot of this type of similar monitoring hardware. Glenn is really into the particulate monitoring. So there's a number of different groups that provide that monitoring expertise. For things like an emergency situation, so ammonia is a big concern for us. There's ammonia in the cooling loops on the US side of the ISS. I don't know if y'all are aware, in January we had a pretty big scare, a false ammonia alarm. There is enough ammonia in those loops to be potentially deadly to the crew. So it is one that we have special monitors for, we have special masks for, and again, that was a collaborative effort, but primarily the EC engineering group here developed that hardware to protect crew. So. lots of folks involved. Any other questions? Thanks, guys. Okay, so the other thing that we do that you might see and might interact with us is actually doing an assessment for health hazards in a payload or a system. And so we will assign it a toxicity hazard code, and that gets rolled up with the hazard code that comes from the biosafety group, and as well as the flammability potential for that chemical. And it gets rolled into a combined hazard level, and that gets labeled on your hardware, and it causes you all kind of problems. No. So it informs safety about the levels of containment that you're going to need for that hardware, because it tells them how dangerous it could be. And then it also informs operations and crew and BME on cleanup procedures. So safety does everything that they can to make sure that it's properly contained and it never gets out and crew doesn't have to worry about it. But if it does, then the crew knows how they should respond, what type of protective equipment they need, what type of cleanup materials they need, et cetera. So we look at the chemical that's in your payload, say. So is it ammonia? Is it formaldehyde? Is it water? Right? And a lot of people will say, well, I don't have a chemical, I just have water. Okay, well, water in and of itself can be toxic. There are people who are compulsive drinkers. They cannot keep themselves from drinking, and they can kill themselves because you get your electrolyte balance off, and you can actually overdose on water. So the dose makes the poison is the tenet of toxicology. But what people typically don't think about, we say, okay, just water. Well, do you have a biocide in that water? Silver or iodine or something? Well, yeah. Or, do you have OPA in that water? Do you have, and as we start talking to folks, they realize, oh, yeah, there actually are chemicals in here. So what is the actual chemical composition of the fluid or the gas that you're using in your system? Then what is the concentration, right? So if I have a 1% solution of hydrochloric acid, it's bad, but it's not nearly as bad as 100% hydrochloric acid, right? So concentration makes a difference as well. And then the volume. So depending on what type of chemical it is, if it's something I'm going to inhale or ingest, then the concentration makes a difference, right? What frustrates a lot of people is for fluids, for liquids, when I'm on the ground, I don't have to worry about it so much, right? When I'm pipetting and oops, I spill it on the bench, I can just wipe it up. When I'm in space, it's now floating, right? So I have to worry about eye contact. And that's the one that gets us. It does not take you don't have a lot of fluid in your eye, so it doesn't get diluted very readily. And if you do get it in your eye, and it's something that it can cause irritation, that becomes a problem. So a lot of fluids end up being eye hazards at very small volumes. And so you might get a hazard rating that you don't love, but that's the reason for it. So we look at both the irritancy potential, like I say, if it's going to cause irritation to the eye, is it something that resolves itself pretty quickly? I can go swimming in the Gulf of Mexico and I open my eyes and it stings and it burns and it might end up red, but it's not going to cause me to lose my sight for a period of time, versus something very caustic like pre-treat, urine pre-treat, then I need to be really concerned about it. So the other thing we look at is systemic toxicity, and those are things like, is it going to cause a cancer? Is it going to cause a liver toxicity? Is it going to something systemic rather than a point of entry irritation effect? Does that make sense? So things will get assigned to these different hazard levels. And if I'd had my say, the system would be arranged a little bit differently, but it's the system that was developed. It's a good system, but it's a little bit of a misnomer to the system. So a 0, if anybody's familiar, safety has just come out with some new hazard classifications. So 0 is equivalent to their new marginal, we call it negligible hazard. So we in Tox we shy away from calling anything non-hazardous, but this is basically the lowest hazard level. It's something we're not really worried about, right? crew doesn't even necessarily have to wear PPE to clean it up. They're certainly welcome to if they want to, but it's not going to cause them any major irritation. A 1 falls into the critical category from a safety perspective. So this is something that for a short time could cause them a potential concern. So if it's an eye irritant, it could cause them enough irritation that if I'm landing a vehicle when I have this stuff in my eye, it could be a problem. I'm going to have to do something about it. I'm going to have to wash it out. I'm going to have to, but it's not going to cause any long-term eye damage. 2, 3, and 4 are all potentially catastrophic from a safety perspective. And so that's where the misnomer is. Everybody sees this stoplight system and 2, 3, 4 make you think increased severity, right? 2s, 3s, and 4s are all potentially catastrophic. They're just potentially catastrophic for different reasons. So 2s are potentially catastrophic for that irritation reason. So these are things like pre-treat solution or a formaldehyde or a glutaraldehyde that if you get it in your eye, you're going to have some potential for major issues and potential even for permanent eye damage. So these are things that we really want to pay attention to. They're battery acids. They're things that when you're cleaning it up, we want to make sure that you have goggles on, that type of thing, and they could literally keep you from being able to land a vehicle. So from that perspective, they are catastrophic. A 3 is very, very rare, to be quite honest, because it's something that's containable. So it's a solid or a non-volatile liquid. It's something I can capture, I can clean up, right? But it's not just an irritant. It can also cause some systemic damage. So it might be something like a liver toxicant or something like that. Epoxies tend to fall into this category. There's really very few examples of a 3. The 4, which has essentially been, this is the one that draws the red flags. I won't say it's been banned from ISS because we still fly a few, but it causes you to jump through a whole lot of hoops. And that's because these are things that cannot be contained. So it's typically gases. It's something that once it escapes, I have to wait for the environmental control system to clean it up. I can't just have crew go get a mess up mitt and wipe it down. And it has potential for appreciable systemic effects. So it might cause central nervous system effects. It might cause something like ammonia falls into this category, right? It could be potentially deadly. We had some thionyl chloride batteries that fell into this category that were subsequently removed from station because of that. So again, I want to dispel the myth that 3 is worse than 2 and 4 is worse than 3. They're all potentially catastrophic. It's just for different reasons. Yes.
I think I got 2 questions. So the difference between 2 and 3, 2 is an irritant,
Yes.
and not just an eye irritant. Could be a skin, could be respiratory.
Correct.
So how then is 3 different? Do you ingest it somehow, or does it go through your skin?
So 3 is something that can be a systemic toxicant. So it's not just an irritant to that mucosal membrane. It's something that can cause a liver effect or a central nervous effect, something in addition to irritation. So irritation alone would put it into a category 2. If it then has additional effects, systemic effects, that would bump it up to
We call it
up
either or,
to a 3.
right? We don't call it a 2 and a 3?
Correct. It's one or the other.
Okay. Second question, if a 4 is not containable, but we talk about levels of containment, are you going to talk about how we reconcile those 2 terms?
Yeah, so in general, the rule of thumb is take your hazard level assignment and add 1, and that's your level of containment in general, okay? So if you have a 0, I can just have it in a box and that's good enough, right? I can have it in my cooling loop and that's enough. If it's a 1, I need to now take that payload and stick it in something, right? A Ziploc bag or something. It has to go in another level of containment. For a 2, now I need 3 levels of containment, right? And that's the reason 2s start getting on people's nerves, because now they're saying, well, okay? I have to do this operation in the glove box in order to have that extra level of containment. There are some exceptions to that rule, right? So I mentioned that battery electrolytes fall into the 2 category. Well, you can't have 3 levels of containment around a battery. It's actually more dangerous, right? You need them to have airflow. You need them. So safety takes those types of practicalities into consideration. And there's separate things. There's testing that you do to ensure that the battery is intact. It's not going to degrade. And so there's a separate set of safety testing measures that you do in order to counterbalance the lack of containment that you have. So I said 2, 3, and 4 are all catastrophic. Technically, 2, 3, and 4 all need 3 levels of containment. So that's where that rule of number plus 1 kind of falls down. So you don't have to have 4 levels of containment for a 3 and 5 levels of containment for a 4. You still just need 3. But, as you mentioned, a gas is not containable, right? So then that becomes, you have pressure vessel classifications and testing and things to make sure that your pressure vessel has safety devices on it that are going to keep it intact, that you're not going to get the exposure in the first place. It's also something that we look at to see, is this a gas that the environmental control system can scrub? So I can't have crew go clean it up, but if my environmental system can clean it up, then it might be something that's allowable. Again, 9 times out of 10, if you get assignment of a 4 on your particular chemical, it's probably not going to fly. If it is, then there's a whole bunch of extra hoops that it has to go through. Does that answer your question? Okay.
Valerie,
Yeah.
how successful when we've flown payloads, for example, how often do we have some kind of a situation that falls into, oh, go clean that up, and then what's your feel on to the extent that the crew actually calls that down or reports it, as opposed to we find out about it later?
After the fact. So I would say almost exclusively I find out about it after the fact because it's taken care of operationally. So BME is the one who is primarily responsible for cleanup and those types of things, and then they let us know after. Because this process is already in place and they have the information they need to be able to take care of it. When I get called in the middle of the night, it's because it's something that didn't have a label on it or it came from an unknown location. They don't know what it is. Let me slip through to this. Yeah, here's one. So these are the calls that I get. They called out and they're like, there is goop coming out of the water heater on the Russian segment. Should I be concerned about this goop? So typically what we will do, if it's an unknown substance and it's a containable solid or liquid, we will default to a 2 because that's the safest thing to do if we don't know what it is. If it's a gas, we will default to a 4, although there shouldn't be 4s up there with very few exceptions, ammonia being one. And I threw a nod to micro as well. They cause us trouble.
You guys cause us trouble.
But there's actually all kinds of sources of toxicological events on board. I would say in general, and I don't know how we're doing on time. I need to, you'll give me the, okay. We have a really good record. I think safety does a great job of designing payloads and systems and making sure that we don't have a lot of issues. But we have, I would say, fairly routine, small issues. And as station is aging, I would say we're getting more issues. Like we recently had the chip system for the ammonia detection kit. It's a little electronic, it's still the Draeger tubes. So they have these tubes that they can break and expose to the air. They actually have a pump that sucks in air. And if there's ammonia there, it has a little purple line, indicator line. But the crew has to look at that and they have to read that purple line and decide whether or not it goes past a certain, so there's potential for human error. So there's this mechanical device that uses the same system, miniaturized tubes, but it's an electronic reader. So you expose it, you stick it into this reader, and then it displays a number rather than crew having to read it out. So it's kind of a backup. crew went to change the batteries in that the other day, and we had a situation where batteries hadn't been pulled from the battery pantry. And so we had 4 different batteries that were all from different lots in emergency hardware, which is an issue in and of itself. But we had corrosion on the batteries, and one of them had actually ruptured inside the device. So, those types of things happen relatively routinely. I would say maybe once a month or so. But they tend to be not major catastrophic issues. Fortunately, we have had very, very few major tox issues.
So Valerie, you have 50 minutes, and so I'll give you a sign.
Okay. Oh, all right. We're doing okay then. Okay. So I will actually go on to talk to you about some of those incidents that we've had. This is probably the primary, the worst tox event that we've ever experienced, and fortunately it was quite a while ago. So during the Apollo-Soyuz program, on the return of the Apollo capsule, the drogue chute deployment that slows the capsule down on its reentry, it didn't deploy appropriately. And as intended, the retro rockets fired to slow the capsule down as a result of the chutes not deploying properly. The unfortunate thing is the capsule, very similar to Orion, is at reduced pressure. And so when it splashed down, there's a snorkel fan that opens it to external air. It sucks in external air to equalize the pressure so that they can actually open the hatch and get the crew out. In a standard, normal, nominal landing, that's the appropriate thing to do. When you have just fired rocket engines and have rocket fuel surrounding your capsule, not the ideal situation. So that snorkel fan opened, sucked in hydrazine into the cabin, and the crew were actually exposed to that rocket fuel. These are estimates. We didn't actually have monitoring devices on board. So these are estimates based on the amount, the duration of the rocket firing. And so just take these for what they're worth.
Fuel or fumes?
Vapors. Not the actual fuel, the vapors. And when they opened the hatch, one of the crew was actually unconscious. And 2 of the crew spent several days in the hospital with upper respiratory issues as a result. So this was our worst case. We haven't had this since. This one makes me nervous. As I mentioned, Orion is designed very, very similarly. And we strongly encourage them to have some type of monitoring device in either external to the vehicle or in the snorkel itself, so that wouldn't open if there were hydrazine or nitrogen tetroxide in the surrounding area. Unfortunately, that's not a feasible option, so what we're looking at right now is a handheld monitor that crew will have inside. They will be suited on reentry and breathing oxygen, so they can look at that monitoring device once they've landed and that snorkel has opened to be sure that there's not any of these vapors in their environment before they doff their suit. So we at least have learned from past experience.
Just a historical reference, that event will be 40 years ago sometime this week.
Ah, thank you.
The launch was last week.
Other somewhat famous, I guess, things that we've had happen, if anybody's read Dragonfly and Jerry Lininger's account of his time on Mir, he describes this. So this was an SFOG, an oxygen candle. This is an oxygen generator that actually ignited. So this was an open, frank fire in the cabin, which was dangerous from the perspective of an open, frank burning fire, right? But what it turns out is it's actually kind of interesting toxicologically. He had these sorbent tubes, and they rotated. So he could take one, and it would take a sample, and then a week or a month later, you would rotate it, he could take another one. And so the goal was this systematic sampling on Mir. During this event, he had the foresight to, on his own, take measurements over multiple hours during this event. So these are actual measurements from MIR in that sorbent tube canister, which was really kind of nice. But what it showed us, so you can see kind of marching along. This again is that t-value chart, and this is based on the 1 hour contingency SMACs. So you'll see that we have that 30-day limit here. Our 1 hour limit is much higher. That's why the t-value is still less than 1. But basically the fire happened. He began taking these systematic samples, and you can see that, again, we never exceeded any of the short-term SMACs, at least for the compounds that were measured, and that they declined pretty rapidly, and we're back to background levels within just a little over a day. So big fire, major event. I'm not minimizing the event, but from a tox perspective, the exposures that they had were actually pretty minimal. Now, contrast that with the BMP had a small paper filter in it. And that has since been replaced. Again, we learn. It's been replaced with a metal filter. But what happened is it's one that alternates. So you're baking one side off while the other side is collecting contaminants, right? And then you heat it up and you bake off those contaminants and you regenerate it. And so it switches back and forth, side to side. And something happened and it got switched at the wrong time and it overheated. And that paper filter that was between the two actually overheated. And they got this little puff of smoke, right? So this is when we tell crew, just because it doesn't look like a big deal, doesn't mean it's not a big deal, right? So this huge open frank fire, not really a huge deal toxicologically. This little puff of smoke from paper ended up being an indicator of the overheating of the contaminants that were on that baked thing. They got out into the cabin. Crew started having symptoms before they started measuring things. Their estimated carbon monoxide levels were about 40%. So smokers typically walk around with about 15%. We start being worried. Our flight rules try to keep things, the CO mask don and doffing limits are based on keeping the carboxyhemoglobin at about a smoker's level. So 15 or below, 15% or below. We estimate that they got to about 40% here. So it was a big, big deal when they actually started measuring, and this is just two different measuring devices. You can see that the concentrations were up close to 700 ppm. Our mask don and doff limit is 200 ppm. So teeny tiny fire, big, big deal. So we try to tell them, don't just look for the smoke. Use the monitor, pull out the monitor, it's there for a reason. Any other?
There aren't alarms then, that's not a...
In this particular case, a smoke alarm wouldn't have let them know. So yeah, they have to use some visual reference to see, oh, there's a potential event. I need to pull out a monitor and check it out. All right. Change gears just a little bit and talk about off-gas testing. Also something you might run into if you're developing a payload, because we do this on the individual payload components. But then we also do it, our job primarily, White Sands will generally do the individual payload off-gas testing. The goal being that all of the materials individually are not leading up to a combined problem. And we test that by actually looking at the enclosed vehicle that once it's packed to make sure that we don't have levels that are going to build up over time, right? So especially in a cargo vehicle that doesn't have its own environmental system, that's not cleaning stuff up, as soon as we button the hatch on the ground, the entire time between then and when it docks and the hatch is opened on station, it's building up these chemicals, right? So if anybody's been in a brand new building, right, or that new car smell that everybody likes, that's off-gassing. That's the glues in the carpet. That's the plastic in your new vehicle. It's probably formaldehyde that you're smelling. So all of the soft goods primarily, so not the metallics, but the soft goods that you have in a vehicle are going to contribute the same types of things. So the same types of materials in spaceflight are going to do the same thing as they do on the ground. In a lot of cases, something like foam packing material, which I will talk about a little more, we can do things like bake it out, intentionally heat it up before we use it as a packing material so that we intentionally off-gas those components so they won't build up as much in the spacecraft. So we do this test before every module of ISS went up, as well as new visiting vehicles, so that we get an idea about the components in that. Typically, the test has 3 time points, and the duration of the test depends on the duration that is going to occur between that hatch closure on the ground and hatch opening on orbit. So for a typical SpaceX vehicle, when we first started, it was it's only 2 or 3 days between. Right? You might have up to 10 days in an off-nominal situation. So we require this test to be at least 1/5 of that total duration. So if you have 25 days that you're going to be buttoned up, your test has to be at least 5 days so that we feel comfortable extrapolating out. And so typically you would take a baseline right immediately after you close the hatch, draw an air sample, see what's in there. We typically draw a sample in the ambient air in the processing facility as well, so that we get an idea about what's there. At the midpoint, in a 5-day test, about 2.5 days, and then at the end. And typically, it's a pretty linear increase over that short duration. What will end up happening with off-gassing is that eventually you plateau, and you generally will get to a point where you're no longer off-gassing at a linear rate. But we will typically just carry this out linearly, even though we understand that it's probably going to plateau. That's a conservative predictor. So if this is where you stood at day 5, we will extrapolate that out to say at day 25, here's where you are expected to be. And then it's not a pass-fail. So I don't have the hammer that says, you shall not fly because you're going to exceed a certain number. What this does is help us inform crew ingress. So if we see a contaminant that is going to be at higher levels than we would like, what we might do is have crew go in, set up the IMV, and then leave the vehicle until that IMV can dilute that air with station air. So we always say dilution's the solution to pollution, right? So you take a very small cargo vehicle that's only 10 cubic meters, and these contaminants can build up to fairly high concentrations over a few days. But if we can stir that air with station background air and get it through the environmental control systems on station, it gets cleaned up pretty quickly. In fact, we've seen some of these vehicles, they clean up so quickly that within about 20 minutes, the air doesn't look any different than the background air. So we'll do this test on the ground and we'll have a prediction of what it's going to look like. But then we also have crew go in, and we have these little, what we call grab sample containers I mentioned earlier. They look like hairspray cans to me. They were redesigned so they would fit in Soyuz, and they have an actuator on the top. They're under vacuum. They literally just suck an air sample in. So as soon as crew opens the hatch and as reasonably quickly as possible, they'll go ahead and take an air sample. And what we've seen, especially with the small cargo vehicles, is that it really doesn't take much time at all. If there's any delay, if they are taking photo ops or they're, and we get a 5 to 10 minute delay in that sample collection, it really doesn't look any different than background ISS air because the air turnover is just so rapid. So why is this any good? Well, one thing I had mentioned was that foam packing material. So the HTV, the Japanese transport vehicle, actually had pretty high levels of carbon monoxide reported during their off-gas testing. We determined that the foam, the packing material, was their primary source. And so they implemented a bake-out procedure of that foam prior to actually packing it into the vehicle so that we wouldn't have a problem with CO buildup on ingress. And CO in particular could be an issue for us because these cargo vehicles don't have an active fire detection system, and CO tends to be kind of our canary for fires. And so crew will typically go in on first ingress with a CSACP, which is a combustion-specific analyzer, a compound-specific analyzer for combustion products. And it measures CO. Well, if you have a high background level of CO from something other than a fire, you could go into the vehicle, see a high level of CO, and misinterpret that as a fire or smoke issue. So this is definitely one we wanted to take care of. We also identified a leak in the Dragon vehicle's coolant system. And it's a very, very tiny leak relative to their overall system. So it wasn't seen as a partial pressure drop. They would never have noticed it in any of their telemetry data. But we saw an increase of this compound that we had never really seen before in any off-gas test. And it kind of looked like it accumulated over time, so we assumed it was an off-gas product. Well, when we took that first ingress sample on board, it had increased significantly, well over what we would have expected based on off-gassing. So we went to them and we asked them, hey, we've identified this compound, we don't know the source, and as soon as they saw it, they said, that's our cooling fluid. And it literally, all it took was the tightening of a bolt, and they were able to stop that leak, and we had significant, like, order of magnitude reductions in the amount of this compound that we saw at the first ingress for their subsequent vehicles, and now it's below detection. So, yep.
I gave you some erroneous information.
Okay.
I didn't realize you had another speaker who was going to tag team with you. The whole 50 minutes was, so you got 5 more minutes. You said you got 5 more minutes, and then the other person.
Right,
that would
okay.
give them a chance
Her
to have
full
at least
time.
40, 45 minutes.
Good.
So, right.
I want to jip you.
I'm going
But
to
you
ask
have-
anyway, though.
Yeah, go ahead.
So who does these tests, let's say in the Dragon vehicle? Do you, NASA, do that? Does SpaceX do that?
So we do that in collaboration with them. So we've actually developed joint test plans so that we have access to their vehicle and their facility with Orbital as well. So to date, it has been done by NASA JSC Toxicology. They have the option to utilize outside sources, and I think Micro is an example where it was a collaborative effort for the first test, and then they've actually utilized a different source for their subsequent tests. The compound list that we look for in these types of tests is pretty specific, and JAXA and Russia are really the only laboratories that do this type of testing. It's possible, it's plausible that they could get an environmental lab to do it, but it would be specialized and it would cost them a lot more. So, and for right now, this is a primary impact to ISS and their environmental systems because it's diluting into station. And so ISS has been willing to take the burden from a funding perspective and just have our lab do it. For the crewed vehicles, it might be a different story. All right. So I just want to wrap up with a little bit of water. I'm so air focused because that has been my primary focus since I arrived, but a couple of years ago, we actually consolidated the air and water groups into a combined toxicology and environmental chemistry group. So we've consolidated, my reports actually have both air and water now. I'm still learning the water side, so I apologize for not giving it its fair due. But luckily, water is also a little less of an issue generally for us than air. It's fairly controlled. We have some unique situations, and one I will tell you about, well, one everybody's pretty familiar with is the high silicon in the EVA water that led to the almost catastrophic incident in the suit with Luca. So we have to worry about the ground supplied water and contaminants that are in there, and sometimes even contaminants that we don't think about. We learn as we go. But one of the things, I mentioned that we measure the total organic carbon in the water pretty routinely. This gives us an idea about general contamination of the water. And so typically, when we're measuring it, we're getting levels that are below the reporting limit. So we're quantifying numbers, but these are These are guesses because they're below the true reporting limit. But you'll notice back in 2010 was the first time that we started getting this spike. And it was a pretty steady increase. And we have it pretty routinely, and we continue to have it fairly routinely. We didn't know what it was at this point in time. So had to launch an investigation and try to determine what the compound was that was causing this increase. It turned out to be dimethylsilandiol, DMSD. Basically, it's a siloxane compound. It comes, we think, from compounds in the air that result from personal care products. We see these types of compounds at pretty low levels in the air. In the recycling system, in the water recycling system, there are filtration beds that maintain this at very low levels for a period of time, and once they become saturated, this starts breaking through. Fortunately, it's not very toxic. So this is our screening level for the total organic carbon. This number is based on formaldehyde, which is our most toxic compound of concern for the water. The limit for this particular compound is actually 3 times this, or 9,000 ppb, microgram per liter. So we can actually get much higher than the screening level for that particular compound. It was an unexpected thing. It ends up being a kind of nice canary because it is one of the first compounds that we see break through the filtration beds. It gives us an indication it's time to change them. So it's like your air filter in your house, you know, when you see that you can't see through it anymore, it's time. That's the kind of the thing here, right? This starts breaking through. It's not a very toxic compound. That's good news. We don't have to worry about it, but it tells us it's time to change the filter. So with that, I will just end with our other consideration is particulate. I mentioned Glenn is really involved in that. We worry about dust when we start thinking about exploration. We had a huge effort to set limits for dust on the moon, and now we're thinking about it for Mars as well, and that's why. About once every 10 years, Mars has a global dust storm like this, so going to be a major tox issue. So thank you very much, and I apologize to Sarah if I ate into some of her time.
I gave you all enough time.
Good. All right. Thank you so much, guys. Appreciate it.
I'll just give you a bit of a background on me, as Valerie did about her. I am Sarah Castro, and I'm with the Microbiology group. I did my undergraduate work. I'm from a very, very small town in Kansas, so I did my undergrad at Wichita State University, which, unless you follow college basketball, you probably haven't heard of. And then in looking for graduate school, I was one of those kids that went to space camp, as did Valerie, and was always all about NASA. So I fell in love with microbiology and undergrad, and so I was really looking for an institution that would combine, you know, a very excellent microbiology department with a NASA connection. And the University of Texas Medical Branch down in Galveston did just that. So that's where I did my PhD, and I actually received a fellowship to do a lot of my graduate work here at JSC. So that's kind of how I got my foot in the door, and was able to really focus on microbial aspects really relevant to spaceflight. And then, similar to Valerie, took a contract position after I graduate, and about a year and a half ago, joined the NASA side. And I have 2 counterparts, Mark Ott and Dwayne Pearson, that I work with, and then we have an amazing team of probably about 14 people that make up our lab. And so I'm going to talk to you a little bit today about what our lab does. I'm also very passionate about research, so I have to talk to you about that. I just have to. And also, I feel like microbiology is one of those things, and we're going to talk about why, that really makes it into the headlines involving things that NASA does. So I want you guys, when you go back to have dinner with your friends or your family, to be educated about these things and be able to, you know, tell them when you hear it in the news, don't necessarily believe it. So those are kind of some of the things. I just gave you my outline that we're going to talk about. So microorganisms, kind of like Valerie said with tox, you know, most people at NASA, I tell them I'm a microbiologist, and they just kind of look at me like, what? Where are you at? What building do they stick you in? Because you don't think of it being something that's very relevant, and it is. And these, you know, every time we send a crew member, we're sending all kinds of other life forms with it. And so these are things that include bacteria, fungi, viruses, archaea, and protists. So kind of the gamut of small single-celled things. And when I go and I talk to students and younger audiences, they something so small, you often don't think, what is the big deal? And I tell them that the bacteria that live in and on you outnumber your own cells 10 to 1. So you're really only 10% human because you're 90% microbe. They always kind of are grossed out by that. And I don't think they believe me, but it's absolutely true. So for about every 100 square centimeter of your skin, you can have anywhere from hundreds to thousands of microorganisms colonizing you. When you drink water, even bottled water, you're drinking upwards of 100 microorganisms per mil. So we don't live in a sterile environment. Our spacecraft are not sterile, our crew are certainly not sterile, so it's something that we have to deal with and really think about as we're planning our spaceflight missions. Because some of these microorganisms, I'm sure as you've all been sick, they can become very dangerous. So why do microbes make the headlines? And I believe they have a very short generation time. So I can take one cell, and I can grow that into a whole population overnight. They're able to thrive in extreme environments, so you can't ever get rid of them, no matter how clean or sterile you think you're operating, you're not. And they are at the center for a lot of the hunt for life and a lot of these astrobiological investigations. So really there's a lot of interest in them because every time we look in some new extreme environment that we don't expect to find them, we find them. So we're continuing to learn, and we're really, really just scraping the surface on what we know. So with that, I wanted to kind of jump in. And so I've gone through and I've picked some headlines that have been in the media. And so I'm actually going to give you the headline, and then we're going to kind of talk about whether it was fact or fiction. So feel free if you have thoughts or you want to jump in or you've heard something or have questions, let me know. So this one, I would feel like you've all heard about, but a researcher, this was NASA-funded research, came out and said that she had found an alien arsenic bug that was really going to expand the way we thought about life. So this is Mono Lake in California, and it does look very alien. It looks like it's a very different, otherworldly looking place. And so Dr. Wolf Simon, she noted that she found a bacteria that was unlike anything else. And the reason is because all of us, microbes, animals, plants, you and I, our DNA is the same in that we have bases, A, G, T's, and C's that are connected to a phosphate backbone. And all of us have this exact same scheme for how our DNA is within our cells. Well, she said that instead of that phosphate backbone that's normal, she found a bacteria that used arsenate instead of phosphate. So this would have been a whole new paradigm in the way we think about DNA and how it replicates. And so when this came out, there was huge uproar, and it was really exciting. So does anybody know, was this fact, was it fiction? It was fiction. She actually, as is common in our field of research, when you find a new strain, after you've done your investigations and you've published your first article, you make it available to the rest of the public. So other researchers then were able to get this strain, and a lot of the tests that she did weren't the ones that we would necessarily do to show that DNA, that the arsenate was truly incorporated in the place of phosphate. So there were some very basic control experiments that were left out of her original publication. Since there's been a retraction, and there's a lot of, it's just interesting to read the back and forth because people were very heated up about this because it changed the way we really look at molecular biology. So the next one, this was very recent. I actually heard about it on the radio on my way into work one morning. So it was claimed that there was plankton on the outside of the ISS and that it was proof that life on Earth came from outer space. So this was back probably this past spring, 2015. And so Russian officials said that cosmonauts had discovered plankton on the outside of the ISS. So I don't know if you have any thoughts about what might they have really found that led them to make this conclusion. Does anybody, any thoughts? Pete probably does know because he works with our international partners. So it wasn't necessarily that it was fiction, but it wasn't quite fact. I believe this was kind of sensationalized. So what they did was they had crew members out on an EVA, and they had big kind of wipes that they collected a sample from the outside of the ISS. Well, it's not like they then tried to culture that, because that would be very difficult to culture microorganisms off. We wouldn't even know how to recreate those conditions. So they took that wipe that they had used to collect a sample from the outside, and they did DNA testing on it. So they extracted DNA from that whole wipe, and they did what's called PCR, where you go and a very small amount of DNA can be amplified over and over and over to make it a large piece of DNA, or a large amount of that DNA. And then they sequenced it to see what was there. They found DNA that was similar to microorganisms that we would expect to see in the ocean. So it wasn't that they really found plankton, they found DNA that resembled, microorganisms of the sea. So the media then made a few jumps to come up with this. And so if I were to take a sample from this table and extract DNA, I would find all kinds of stuff that was there, because it's just everywhere. DNA is a very stable compound, and it's just in the environment. And once it gets there, it's there. And so we actually do a lot of work with some of our collaborators out that do work on robotics and the OSIRIS-REx mission, because they're not concerned about microbial contamination. They're concerned about any kind of biological, organic contamination, including something like DNA. So these are all things that my group kind of does to help answer some of these questions as to what's there beyond just microorganisms. So the next one, space can turn bacteria into supercharged mutant monsters. So one of our collaborators at Arizona State University has successfully routinely flown Salmonella typhimurium, and she got a lot done when shuttle was flying, and so she was able to fly it on 2 separate shuttles, and that was a big deal to be able to repeat your experiment. And when she put out her report, she noted that the bacteria that had been flown in space was much more virulent. And that is fact. It's not a space-charged mutant monster. That was, again, the media helping us out with the headline. But what she did find was that when her team was there at KSC as soon as shuttle landed, and they would go and they would collect the bacteria that had been in flight. They had ground controls that were growing at Kennedy, and they infected the mice immediately. And what she found was those mice that had received infection with the spaceflight grown bacteria, it took less bacteria to kill them, they died quicker, and all the classic things that we look for to say that this strain was more virulent after it had been in spaceflight. I know everyone has to have heard about this one. So this is the famous meteorite, Allen Hills 84001, and it made the headlines when NASA announced that what they saw that they believed was microbial life. And this is a Martian meteorite, so they know that it's from Mars. And this even, and I don't remember this, but I guess when I was going back and doing my research about it, Bill Clinton actually came on and was a big TV announcement to say that we believe we have found life that came from Mars. So does anybody want to take a stab at whether we think it was? Any answer would have worked. We still don't know. And this is still hotly debated here amongst the researchers at JSC. And so you'll have one group that'll come out and say, oh, no, this is contamination that just came from Earth after the meteorite had landed on Earth. The NASA scientists will come back and say, no, that contamination, it doesn't resemble anything else we've ever seen. And we haven't seen anything like it in other meteorites. And it's so ingrained within the meteorite that it couldn't have just got there after the fact. And then the community, someone else, a conflicting researcher will say, no, you can recreate this in a lab, and we've seen similar things. To which the NASA researchers who believe that this is extraterrestrial, they will come back and they say, well, it looks like there are these magnetite crystals, and they were within these carbon globules, and that we see magnetotactic bacteria do the same thing on Earth, so we think this is what's happening, and you couldn't recreate this in a lab. And then, that's what they'll say. You couldn't recreate this. There is no other, natural setting that would allow you to do this. So what is the conclusion? And it's anybody's guess. It's one of the oldest meteorites we've ever found, and lots of people say, well, if there was life on Mars, it probably floated by this rock, and you can't just use morphology to really say was that life or not. So part of this is still over of this original sample is still over in Building 31 in the Meteorite Receiving Lab. So from like a microbiologist perspective, it's a really cool piece of history. And, you know, the questions are still out there for all this. So that's all I'm really going to talk about in terms of the astrobiology, because we don't focus on that here. We leave that to our colleagues at other centers and academic institutions. But I think it's something really interesting to think about, especially as we start looking at exploration class missions and asteroids and other things. So what does my lab do? So the entire goal is to mitigate microbial risk to crew health and safety during the human exploration of space. So we're concerned with human health and we're concerned with vehicle health. So we're going to focus on both of those things. And as I mentioned, we have an amazing team of people with very different skill sets to really be able to look at all these different things, from bacteria to fungi to viruses. So we really can kind of get our arms around any of these microorganisms. So our lab we're really involved in a lot for dealing with very small things. As Valerie was talking about with some of her toxicology assessments, we hold the Biosafety Review Board. So much like her group is going to assign a toxicology rating, we are going to assign a biosafety level rating. So with a lot of the increase in science that we're doing on ISS, there's a lot of payloads that are including cell lines, animals, microbes, all different things. All of those have to have a BSL rating. So the same thing, how many levels of containment does the crew need to be able to work on that? So my group makes those assessments. We support the center. We get calls all the time that, hey, there's some mold growing, one of the buildings leaked. Can you guys come look at this? Is this something toxic? Or our water out of the water fountain tastes funny. Can you guys come? All of those things my group does. We're very involved in, obviously ISS is our bread and butter, but we're working very closely with Orion and the commercial providers to get going on that next leg of exploration. And then we do a good amount of research, and I'm going to talk about some of that in a little bit. So crew health, and these are things that you can all relate to. These are, as Valerie was saying, catastrophic in our opinions. If you've ever had food poisoning, you know that that's a horrible thing. You have the ability to call in sick to work and stay near your restroom for the day. A crew member does not have that luxury. So we take all of these things very seriously, everything from minor skin irritations to viral reactivation, something like herpes, to gastroenteritis, all of these things that we screen for and we look for. When it comes to environmental performance, this comes to the vehicle. So these are some of our pictures of some of the anomalies. So we'll talk more about the FGV panel and the ZSR panels in a little bit. That was the Russian water line, and you could see that material that's coming out. The crew actually called down and they didn't know. Is it biological? Is it not? Is it just a buildup of organic materials? So that's kind of our job. We put on our detective hats, and from a picture we have to try to figure out what that is. And there's things that often don't, in the air conditioning ductwork or in the portable water reservoir, it's not as simple as it looks. So we make our initial assessments, but then really getting our hands on a sample is really when we can give a lot of information on what that contaminating agent is. So some of the adverse effects, and I'm sure this is all something you can think about, infectious disease, toxin productions, allergies, food spoilage, all these things really can cause, a bad day on the ISS. And we're really concerned with some of these things. There is, Valerie and I, one of our colleagues, an immunologist, looks at changes the astronauts' immune system. So you can see now how we all start really working together, because a change in the immune system might make a bacteria that normally isn't a concern, might now make it a concern, or have an effect on a certain chemical contaminant that's in the air. So it really all is a synergy of all of us in the life sciences working together to really try to understand what the risks are. And honestly, we're just now starting to get there, because a lot of our data was post-flight and pre-flight. So we missed that in-flight component of it. So we're really now just starting to understand what's going on. So as I've already alluded to, the sources of contamination on the ISS are the crew, the cargo in the vehicle, and then the food and water. So my lab screens all of these. So we screen the crew members, we thoroughly screen the food, the cargo, the vehicles, everything before it goes up to try to minimize the risk, right? And I told you, we're never going to launch a sterile vehicle, a sterile crew member, but we can do our best to try to clean it up and minimize what potential pathogens are there. So again, just kind of reiterating some of the things that we're doing. We want to keep the vehicle and the crew safe, and we hold requirements for acceptability limits concerning the air, water, surfaces, and the food. We do provide certification of flight readiness inputs, and then we, just much like the tox assessments, we do pre-flight and in-flight monitoring to check contamination controls. So how well is the crew that's building Orion, how well are they working to keep that vehicle clean? Our methods are really a check of their contamination controls. And then when we do see some of those events, like we have a clog in the water line or visible mold growing, what do? They come to us and say, how to remediate that? What do we do? So those are the big things. So all this starts off, and this stuff bores me, so I'm just going to quickly go through this, is that initial risk definition, right? So are pathogens even there? Is there something that the crew could be exposed to that would potentially harm them? And then if they're exposed, how long, if they're exposed, will they be infected? And all these other factors, just the restraints on hygiene, the not having access to a physician, all these things factor into our risk assessments. And as we get these, we use these to develop our requirements. And so we're very, we put a lot of thought into our requirements and the acceptability limits that we have, because if we're too stringent, if we say the vehicle has to be a level of clean that's hard to attain, we're wasting resources cleaning and rechecking and cleaning again. If we're too relaxed, then we run the risk of a crew member becoming sick or something, microbially leading to degradation of the vehicle. So it's a very fine line we walk in between trying to balance out where our requirements lie and really what should be acceptable. Once we've done that, we take those requirements and our acceptability limits and we apply them towards prevention, engineering controls, and then monitoring and remediation. And these are really the three main things that we want to do, that we want to focus on as we kind of approach the different microhazards involved in spaceflight. So I've kind of mentioned this many times. Prevention is just we want to reduce the numbers and the types of microorganisms that make their way up there. And a majority of these we can rule out long before they ever get launched. And this includes the pre-flight monitoring of the cargo and the environment, the quarantine of the crew, the biosafety review of all the payloads, and the screening of all the foods. So we obviously can't screen every single food, but we take a percentage of every lot that's made and we screen it. And we disqualify some, and we have, things that we look for that would cause that food not to be able to be consumed. The same thing, that's why the crew is quarantined, and I have a slide on that in a minute. We don't want them exposed to whatever their, the general public has or a small child, and then taking some of those things that otherwise wouldn't be up there with them to the space station. The engineering controls, and these are things that we've really learned over time, and how to really do this effectively. And that's just really minimizing those hazards to begin with. So we found that system design is huge. And that if you can involve micro from the beginning, from those initial stages of designing your vehicle, we can really make sure that the right things are done to where you potentially won't have a microbial problem, or it'll be minimized. And that involves things like material selection. Hepa filters. Mir did not have a Hepa filtration system, and when we would get air samples back, they were filthy. We'd see all kinds of things. Yeah.
I don't know if this is on your engineering controls on the previous slide that was the prevention, but like for instance, I know that as we sit in the FACB and they talk about the bags and wiping down the bags, is that something your group gets involved in or somebody else's group?
That's our group.
And is that part of your engineering controls or part of your prevention? Because I didn't see that on
The issue with the cargo bags, that's part, so in actually cleaning them, that was a remediation. So we saw there was a problem, we need to go clean them. That was part of our initial screening. So we do, just like we screen the food, my lab will go over and they'll take samples, random samples of the different cargo bags. So the big bags that are filled with cargo that are going to send, we're going to sample the outside of those bags. We're also going to sample the hardware. We're going to sample a percentage of everything that goes up. And so I think probably the one that got all that you're talking about was when I think it was launched on, I think it was with on the ESA vehicle, the cargo bags, after they were already docked to the ISS, our report came out and said that some of those cargo bags had exceeded our acceptability limits. And so there was a big to-do about having the crew open them and then potentially bring contaminated bags into the rest of the ISS. And so we had our crew go in on ISS, don PPE, go in and clean those bags. So these bags were actually, while they were packaged here, they would be sent to Kourou in French Guiana, where they would be loaded onto the vehicle. So somewhere between when they would leave our processing facilities here at CMC and end up in the jungles of Kourou, they would become very contaminated. So what we did is we sent members of our laboratory there to their facilities, and they put on all the gear and they went in and they cleaned all those bags prior to loading on the vehicle and launching. So that was what we did after the fact. So then it went from our initial screening to remediation as a way of doing prevention. And so we did that for all of the flights after that would launch out of Kourou. So, and it's not hard to imagine. It was very humid. It was a jungle. Their conditions their facilities weren't the same as ours, and so there was lots of places that the contamination was coming in, and that is really hard to rule out. But what we could do is have our people go and clean those bags before they ever got launched. So that's what we did. So those are the things that we learn as we go forward. We've seen very similar things with SpaceX down at Kennedy Space Center. They were supposed to be doing a lot of their sampling in a closed kind of environment, but we realized their closed environment was a cloth kind of hanging between where they were taking their air samples and the outside environment. Well, of course, all of their air samples were coming back, and they were blowing all of our specs, and the air looked horrible. And it took us no time at all, once we saw what they were doing, to realize this is what's going on. So we can really learn from that and then say, hey, next time you really need to have the hatch closed or whatever you're doing when you do take these air samples. And the same thing with Hepa filters. So we didn't have them on Mir. The counts were horrible. We have them on ISS, and it's very clean air. Like Valerie said, chemically it's very clean. Microbially, it's very clean air that the crew member breathes. Same thing with the water. We have inline water filters. We have biocides in the water. The water that the crew drinks on the ISS is cleaner than about 99% of the water the people on the Earth drink. So it's a very good environment. We've been very successful at implementing the things we've learned. So this is another one I like to ask to this when I give the talk to younger audiences is what kind of materials would you want to build your spacecraft out of? And they all say stainless steel. I mean, they get it. They understand. That's not, unfortunately, how engineers and the people building the vehicles always think. And so they like some of these more soft cushioned kind of walls or carpeting or something. And that's what this leads to. So these are the FGV panels in the Russian segment, and it's like a nice soft carpeted material that they really seem to like. And these are the ZSR panels that are above the galley where a crew eats a lot of their meals. And the crew, they'll see this. They'll see these spots start to appear, these discoloration, and to them it was pretty clear that this was mold. And the ZSRs, it's kind of brown. They weren't really sure. Well, the crew becomes aware of this, and they don't like this. It's just like when you shower, you start to see something growing. Hey, it's time. The crew, the same thing. So they start to complain, and then they start to, when they do our sampling, so air and surface they do every quarter. When they do our sampling, some of the sites they pick are crew preference. So they would pick these sites, and they'd pick some of this or a little spot on the ZSR, and the plates that we would get back would just be full of, obviously fungal and bacterial growth. And so, then it's how do you remediate? Well, they have little disinfectant wipes up there, but that's not going to do a lot of good against these. So it becomes a much bigger issue. And then it's, kind of working backwards and how did this happen, getting to the root of the problem. And come to find out, these FGV panels have these nice bungees across here that when the crew would be done working out or showering, this is where they would strap their wet towel for it to dry. So, in not very much time, you start to see things grow. The same thing with the ZSR panels. they think, no, well, when we're eating or drinking or we do it cleanly, well, a blob of coffee might come out, or some of the marinara sauce might and cause an impaction on the ZSR panels. And those are like a Nomex, they're like a cloth material. And there's a perfect environment for things to grow. So as soon as a food source is available, or something like water in terms of fungi, you're just going to have growth. It's just going to very quickly blossom. And so that's what's happened. And so then remediation becomes a little more problematic, and we start talking about replacing these components, or could we put some kind of plastic covering on the outside that could be easily wiped off. And so these are the kind of conversations we get into after this has happened. So
That's when we ask crew to do certain operations in certain locations.
Yes. And with the ZSR panels, they were really concerned because they had a lot of their public affairs kind of things there with that in the background. And they were concerned about it. Public affairs was concerned about it because the crew, it's their house. They want to keep it looking nice. And so when there's big splotches behind them, so then we help them try to figure out how to clean that up and not let it happen again. So I mentioned quarantine a couple times, and this is, it's famous because of in the movies and what you think of, and it was, the health stabilization program was initiated as it is today after Apollo 13, and you can see that whenever one crew member would have something prior to that, they would all have it, and they would just share everything. And this was because they're having interactions with their family, with their kids, with the general public leading up to a launch. And so all those viruses that are going around, everybody ate the same potato salad that might have been sitting out for too long, all those things spread pretty quickly. So once we initiated that, we've seen a huge drop-off in the rates of infection and things that are shared among crew and things that are taken up to space in the different vehicles. So we've been really successful with this. Initially, it was much more strict. It was a significant amount of quarantine before, quarantine after, especially coming back from the moon. We didn't know what to expect. And now we've obviously relaxed that. There's no quarantine after, but still leading up to flight, we do have a period of crew quarantine to really limit the potential pathogens that they'll be taking up into space with them. So again, I've mentioned several times just the different environmental monitoring that we do, and this is all pre-flight. So this is some of those the things you were asking about. So these pictures are our lab members in the different vehicles. So we physically go into the vehicles and we collect surface samples from random locations and air samples throughout the vehicle to get an idea of how, and again, this isn't really just to say what's there, it's how well did whoever built these vehicles, how well did they do keeping it clean while they were building it. And we have contamination control procedures, our commercial crew providers have those, everybody has those, but how well are they actually using them and how well are they following them? So that's what our checks do, yeah.
How do you guys screen the food?
So we actually go over and they actually bring samples to us. They bring us a percentage of a lot from each. If they make up a new lot of spaghetti, we get a certain portion of that. And our lab actually takes it and mechanically, we have an instrument called a stomacher that kind of simulates, just breaks it down. And so then we actually just do basic microbial, to get how many counts are there, plate it out just like we would anything else.
So it's pre-packaged?
Yes.
Screening, not post-packaged?
We do both. We do finished goods, so after it's already done, ready to go. And then when they're doing R&D, they want to put up a new kind of, I think guacamole was one. They were wanting to look at a new, so as they're doing it, as the food lab is actually working on developing it, they'll bring us the raw ingredients and they'll bring us some of the finished sample. And we actually look at the materials they use too to package it. So we, all along the way, will be taking checks. And then we also go and we take samples from their facilities to make sure that they're staying clean. Yeah.
So did it cause you all a problem when, for PAO purposes, they wanted to fly fresh fruit so that the...
Yes, it did. A big problem. Because how do we deal with that, microbially speaking? We all know that if we go to Kroger and buy strawberries and put them in our fridge, if we haven't eaten them within a few days, they're going to be pretty fuzzy. And so dealing with some of those things, we have acceptability limits and we have requirements for all the food that we're traditionally used to seeing. Food that's been, it's been baked, it's been then dehydrated, it's had all these things done that those things don't inherently remove microbes, but they're processing along the way, keep the levels low. So dealing with something like fresh fruits and vegetables, it was kind of like a how do we even do this? And starting to work on, we know that there's going to have to be things we do to relax some of our requirements, maybe waivers, some things like that. And when I'll mention the research, the food lab has approached us and interested about wanting to give the crew members probiotics. And, a lot of the crew members, they're healthy people, they eat yogurt. They want to eat yogurt. They know that there's a benefit to consuming the microorganisms that are within that yogurt. Well, obviously the yogurt is not going to pass our requirements, but it's a good bacteria. So how do we start to kind of change our minds and start thinking that way? So we've gotten funding to do some basic research by putting those probiotics in their dehydrated milk to see how long is it going to survive. Let's not fly it if it's not even going to survive. And then we'll stress it. We did some simulated gastric and intestinal stresses to see how well it survived. And so we're doing that. We found out recently that JAXA, through a partnership with Yakult, and that's one of those little drinks, that they're going to try to fly that and give it to their crew members and other ones who are interested in participating. So we have no idea what that's going to change. We really don't understand yet what's going to happen. So those are the things we're starting to really deal with, and moving beyond, keeping microbes out. What if we're actually adding them? So as I mentioned, the crew members, they're going to actually go around and take swabs of the surfaces. They're going to process water samples, and they're going to take air samples on the ISS. So air and surfaces every quarter. Water, they're going to do every other month, and they're going to vary between the different ports of the PWD, and we also look at the Russian water system. So I don't know, it's kind of hard to see this, but again, in trying to get people to understand why this is important, this crew member's drinking one that says today's coffee, and this crew member says yesterday's coffee. So you know that when you're drinking the water, that's recycled urine. And so you want to know, that's yours, it's your other crew members, you want to know that that's clean, and you want to know that the water processing assembly is functioning properly and that it's processing it the way that it should. And so this kind of comes back to where a lot of what we're doing in the vehicle is where how well are they maintaining a clean environment when they're building it, how well are the environmental control systems working. So it's not so much of, we know the water's pretty clean as long as the system's working. So in addition to some of the stakeholders Valerie mentioned and customers, the groups that build these are really interested in our data, because to them it's a direct correlation of how well their systems are working. If we see high numbers, they know something's not, catalytic oxidizer isn't working. We see low numbers, they know, yep, that's working, the iodine's being added, the filters are not clogged. So it gives them a good peace of mind too on their systems. So when the crew member does a water sampling, they actually are able to, they culture up the microorganisms there in flight. So they're actually growing bacteria on the ISS, and they can actually count them. And they grow up on this little grid. There's a dye incorporated so that you can actually count how many, after you filter them, how many microbes are there. So that gives us a good idea, based on just numbers, what the water looks like. We have one other test, and that's a Coliform Bag, and that's simply a powder that has a chemical in it that certain coliform bacteria can actually have an enzyme that will change that to make it go from yellow to purple. So if that bag is purple, we have a big problem, because coliform is an indication of a contaminated water supply. So this is something also on the ground that, in countries that don't have the water processing that we have, this is a common test for them. Has their water supply been contaminated? And so it's not really telling us what's all in there, but it's giving us a good indication of how clean the water is. For surfaces, they have two different kinds of growth media, one that'll grow bacteria and one that will grow fungi. And so they look at it and they take their sample. They can either take a swab and put the swab on the plate, or they can actually put the slide right up on a surface that they want to sample, and they allow it to grow for a few days, and then they compare it to a density sheet, and they tell us for bacteria, it's a number, for fungi, it's a letter, so they're not actually counting it, but it gives us a good idea about a 4 or a B, or it gives us a good idea about how clean that surface is. And so those are the checks that we have the crew do. For air, it's very much the same thing. They collect the air sample, and it's 2 different types of media, and it's the same thing, a number and a letter for either bacteria or fungi. And then that tells us, again, are the Hepa filters working, or are all these things happening the way they should be? So we can get the counts on orbit. So the crew member can give us that letter and that number combination to tell us how much is there. But we can't do anything to identify anything. And in my opinion, this is a big problem, because microbiologically speaking, it's almost more important what it is than how much it is. And so we can get the counts, but we can't identify anything, with the exception of were there coliform producing bacteria, which is a large range of different bacteria that can do that. Is the only identity kind of questions we can answer. We actually get all the samples back on the ground, and they come back into our lab, and that's when we figure out what types of organisms. So we have a biochemical method, the VITEC, and then and that does a whole bunch of different biochemical tests to try to figure out, narrow down what the organism is. If that doesn't work, we move to DNA sequencing and sequence part of the genome to figure out what the organism is. So that's how we ID it, and all that happens in my lab on the ground. So what's there? So for air and surfaces, these are this is bacteria and fungi, and kind of just a big chart where we put everything together. And really, the take-home of this is what we see is what we'd expect. These are the types of fungi that we would find in your house, in my office, in our lab. These are the common things. The same with bacteria. Staphylococcus is one of the main ones. Well, all of us are colonized with Staphylococcus epidermidis, some of us Staphylococcus aureus, a lot of different types. So really, this is what we expect. This is very traditional of any environment, any human, any house, anything. So we don't have anything that jumps out. And we've seen that over time, Station has we've been looking at it since it was very first started being built, and it has its own microbiome now that changes slightly when we add different crew members, or would add at the time would add a different component. But it's really kind of flatlined out, and really we have a pretty good feel for what's there using our culture-based methods that we use. The water, the same thing. This is just expedition 34 through 39, but it's the same thing. These are the samples that we got back to the ground. The MCDs are those ones that the crew counted. The archive bag is when we just get extra water back to do our own assessments with. But the same thing, the Ralstonia, the Burkholderia, all these organisms, this is what's in my bottle of water. This is what's in your tap water. These are the things you drink. And again, this isn't how much it is, because you could drink a lot of these organisms and not have a problem. If there were a few E. coli in there, you'd have a big problem. So those are the kind of things that we want to know. But everything that we've seen, it's a very healthy environment, microbiologically speaking. So just to this is more kind of the numbers, so how much is there versus what's there. And really, to me, this is the one that kind of says it the best. So our lab went in and we did some different houses, and we just went in and said, okay, how do the levels look compared to our limits that we have for the ISS? And so fungi is red, and you can see that most houses were at or below our ISS limit. But when you look at bacteria, you can see that almost all of them were over our ISS limit. And we're talking, a log fold over, so quite a bit over our limit. But again, this isn't unexpected. This doesn't mean these houses were dirty. It just means that we're doing a very good job of keeping the ISS clean. So just kind of a quick summary of all the operational stuff that we do. Infectious diseases are a real threat, and astronauts have gotten sick. We minimize that through the different prevention, engineering controls, and then the monitoring and remediation we do. And when we have seen these anomalous events, it's often uncontrolled water, fungal contamination, and we have seen, I mentioned Staphylococcus aureus, that's an opportunistic pathogen that about 30 of us carry around normally, but it's up there because 30% of the crew have it too, and that could cause somebody a really bad day. So we know they're up there. So we have a good understanding of what's there. So then kind of the next part of this, and this is, again, what I'm pretty passionate about, is the research. So we know that these organisms are up there, so what? What does that mean? Does that change versus what I encounter in my home and in my office and my work? Because, and maybe it does, because there's potential that spaceflight in that environment, just like we know it causes changes to the crew members, that it's causing changes to the microorganisms. So that's also part of what my lab does, is really try to understand how being in this environment might change the bacteria or the viruses. So really quick, this is a bioreactor that, I'm going to talk about it in a little bit. So just a quick on bacteria in space. Before Yuri Gagarin ever made his flight, the USSR sent up bacteria to try to understand how spaceflight would affect a living thing. So before the dog, before the monkey, right, we sent bacteria. Well, the USSR sent bacteria. We followed up on some later flights, and really all throughout early spaceflight, the crew members would be culturing these things on board. And as early as late Apollo, it was really pure research that the crew was doing with the microorganisms on flight. Shuttle brought with it an increased ability to do a lot of this. So we really started sending up a lot of different types of stuff. And for the first time with these early flights along with Shuttle, we really started to see, okay, there is a response. These microbes are sensing that something's going on, and they do respond to this environment. We had no clue as to what, why, or how, but we knew that we were seeing the spaceflight cultures look different than the ground cultures. So as I mentioned earlier, Cheryl Nickerson's work, she's at Arizona State University. She's done a lot with salmonella, and that really is the most thoroughly characterized organism in terms of spaceflight. And she's the one who found that it does become more virulent after it's been in spaceflight when mice are infected with it. So to really expand on that work, we needed a way to do it quicker than just continuing one at a time, fly it, which flights are limited and all that. So in the late 1980s, the biotech group out of NASA, the life sciences, developed this rotating vessel that would mimic aspects of the spaceflight environment. So their goal was really create a cell culture analog for spaceflight, and they really developed it for eukaryotic cells, so that you could put in, mouse cells or human cells and really see how those were affected. But of course, then the microbiologists came along and thought, well, let's put bacteria in and see how it impacts them. So we really started using it for that too. And so how these work is you have this system that you fill it completely full of the growth medium, so full of the liquid, and you inoculate your cells in there. And again, that could be bacterial, that could be mammalian, and it rotates. And so it's completely full with fluid. So normally, due to gravity, those cells, they don't have anything to keep them suspended, they're going to settle out. But because this is rotating and rotating and rotating, the cell falls, but then it's carried back up because that media in there it reaches a solid body rotation. So it falls, it's carried up, it falls, it's carried up. So the cell starts to be maintained in this little orbit. And when you can put in beads or something, you can actually see this happening in the bioreactor. They'll just sit there and they won't fall out. They'll just stay maintained in this little orbit. And because of that, they're seeing some of the same things that they would if they were in microgravity. So they're not settling out, they're staying suspended, and they have a very low level of fluid shear going over their surface, which if you were in microgravity, those were the same things the cell would experience. So we've really done a lot to use this system and try to understand how bacteria are changed in being in something like microgravity. So with Dr. Nickerson's work at ASU, she found all these findings based on her work with the shuttle. But to really take that to the next level and figure out what's going on, she put it in the bioreactor. And so by doing that, she found, in addition to all these other things, she was really able to go in and look at the genes and what changes are happening in the genes of the bacteria and look at expression. She was also able to change the nutrients that the bacteria was getting, and she found that was very involved. So she's really starting to delve into the mechanism and the hows and the whys that these changes are happening. My work was with Staph Aureus, and I like this because I think it just kind of, there's still some, does it really change? Yeah, we know it changed astronauts. They have changes in spaceflight. Does it change bacteria? Well, Staph Aureus, and again, that's something that, it's MRSA, the super bug, I'm sure you've heard of. That's this guy. He's normally yellow. When you grow him up, he's usually yellow, and he was actually named Aureus because of that, because aurum is Latin for gold. Well, when I put him in this spaceflight analog, and I grow it that way, it stops producing those carotenoid pigments that make it yellow. So just simply by growing it in this spaceflight analog, it's fundamentally changing its physiology. And so then you can really go in and drill down and start to look at some of the other things. And I think because of this, it doesn't have that pigment. That pigment is something that allows it to be virulent because it kind of protects it from things that our body throws at it to try to destroy it. So when I take them out of that spaceflight analog and I put them in cell culture or human blood and challenge them with those immune cells or immune components in human blood, I find that they're not as able to survive as their pigmented counterpart that was grown as a control. So again, we're really starting to figure out that this environment may cause a lot of changes, and then again, we can do a lot more now, technology, to get into the why, so looking at gene expression. And interestingly enough, even though Staph aureus and Salmonella are very different organisms, we're seeing that they respond using a lot of the same genes, a lot of the same pathways. So again, we're just on the cusp of all this, but I think it's just fascinating what we're finding. So our lab does more than that, those two things. We do look at increased viral reactivation, so it's seen that the astronauts are actually shedding viruses that so once you get chickenpox, you're always going to carry around that virus. Your immune system suppresses it. If it were to reactivate later in life, that's shingles. It's the same virus. We found that astronauts are shedding increased levels of that VZV, the varicella zoster virus, but yet they're not getting shingles. They're not reactivating. So what is it? So there's some kind of interplay between the immune system suppressing it, but they're shedding live virus, but they're not having the pathology. So there's something going on, and that's a very active area of research in our lab. We work with the engineers to, again, this idea of using bacteria beneficially. Can we use bacteria to clean up the water? So these are massive, they're over 6 foot tall wastewater bioreactors. I think they're over in building 12. And they were looking at different ways that if we could add different bacteria to pull out all the organic carbon and nitrogen and some of the other things from the water, that then it could go through reverse osmosis and then be consumed. I mentioned the probiotics and the stuff we're working on with the food lab, and that's really, could we incorporate that into the crew member's diet, and would there be a benefit? We don't want to do it unless we know that there's a benefit, so let's really do the research first. And then the Astronaut Microbiome, and this is a collaboration with Hernan Lorenzi out at JCVI to really look at how does the astronaut's microbiome change as a result of being in spaceflight. And this is something that, we've done a few subjects and we have good crew participation, so it'll be really interesting over the next few years to find out what all that means. And finally, this is a brand new effort, and so I mentioned everything we're doing is culture-based. So the astronauts are growing microorganisms in space. So that's really not the best way that we would like to do that. We would like to be able to find out what the identity of those organisms are without having a crew member, exponentially increasing the numbers of them by culturing them. So this is a project that was funded as one of these 2x2015 Class 1E payloads, so a way to get science or technology on the ISS quicker than the traditional Class 1. So we just got the green light for this in February, and I will tell you, we've already gone through our first payload safety review. We've already done a lot of our initial stuff. I mean, we're cruising along compared to how long it normally takes. So this is the MinION, developed by Oxford Nanopore Technology, and I wish I had one to show you. It's like half the size of a stapler. This is a DNA sequencer. And it is because of this and the technology that we're able to do it. So we're looking at launching on Orbital 5 and having the crew do a DNA sequencing experiment during increment 4748. And we're really excited because this will be the first time, we haven't done any molecular biology in space, extracting DNA, anything, let alone sequencing DNA. So we're taking, in my opinion, huge steps forward with this. And so this is a next generation sequencer in my lab. This is state of the art, cutting edge right now. This is the MinION, the mini DNA sequencer on top of it. So that gives you kind of an idea of how small it is. And it doesn't have a battery again, so that helps us with getting it certified. It just runs through a connection. We're connecting it to a Service Pro 3. And we really just want to test it. Can we sequence DNA in space? Is this even possible? How is the sequencing data going to compare to the ground? And then how well is the crew going to be, how well are they going to be with operating it? And we have Kate Rubens has been involved with all this, and so we have no doubts that that's going to be great because her background is very much aligned with this.
What kind of sample does it use? Is it an air sample or a surface?
For this, we're flying up samples that are ready to go, like samples that are ready to be sequenced. So that'll be the next step of this, right? So how do we take a surface sample and get it ready to go? And so we're working on that. But right now we want to see that this is possible. And then hopefully it'll, air, surface, water, human, anything. So again, I think you can kind of see the benefits to being able to do this. We'll be able to ID something in space and not have to bring samples back, not have to culture things. And again, DNA is DNA is DNA. So while this will help me identify microbes, this will help the docs look at things that they want to look at in the human genome, look at different countermeasures, look at certain radiation hotspots. So it can be used for a lot of different things. And that's actually it. So I think it's good job security, as we're always gonna sending microbes with us wherever we go. That's it.
Oh, thank you. Dr. Meyer, Dr. Castro, thank you all for your.
I do have a question. So talk a little bit about how you interact with rodent research.
Mm-hmm.
Sampling beforehand, in flight, and concerns.
Yeah, so we actually have gotten pretty involved with that. They contacted us. It started initially as the rodents need water. Can you help us get a hose, from a sterile hose to where we can get the rodents water from one of the water supplies on ISS. So we started off just by, we'll help you, we'll autoclave your hoses, we'll help you make sure your hoses stay sterile. It's kind of since evolved into, we're working on developing a specific pathogen-free list to where we look at all the different organisms that might be associated with the rodents and be able to assess that in terms of the biosafety levels. And the rodents can't have these organisms, these are acceptable. All the way to the most recent one is, well, you guys do the crew members' food, we want you to start sampling the rodent bars that we're going to feed them. So that's the latest. So it really started with, can you help us get them sterile water, to now, can you make sure their food's good enough? They want to use the same standards for the crew, which we're fine with that because we don't want to put higher levels of microbes. And then we want to make sure that those rodents are obviously not carrying something potentially dangerous. So, yeah, we've done a lot with allergens. I always kind of forget that because it's not really microbial based, but right now we're looking at changes in the allergen levels in the ISS. So we're working on getting some of the vacuum cleaners back, and we take the dust, and we have some of our collaborators at Johns Hopkins who have a standardized test for that, give us different levels of allergens. So we have some baseline samples, and then we're going to start looking at, do that levels of allergens elevate as now that we've started having rodents there. So we won't know that until a little bit further down the line. But
All right, so once again, thank you to both of you, and we appreciate all of your information. The Microbiology Lab Tour, today is the 21st. The Microbiology Lab Tour, which is Building 37, 1022, is going to be on 7 and 28 at 1 o'clock. So July 28th at 1 o'clock.
They're combined as well. We'll just do a rotation.
Oh, so it'll be a combined tour,
Yeah,
micro
we'll do
and
air, water,
Okay,
and micro, and we'll just, depending on how many folks are there.
okay.
just split and then swap.
All right, so Ruby, is that in Saturday? They have to sign up for that one as well? Okay, so if you're